we're going to look at composition of functions. So really what that means is we're going to insert a function into another function. So the way it's written here, f of g of x. That's how that is read. Now, we could also say that that looks like this, f of g of x. You know, think like we can say f of 2. Well, we're inserting a function as the input now, okay? So the domain of composite functions means that whatever is in the domain of the input function is the domain of the outside function, okay? Because if the function in the inside has an issue with its domain, then it'll have an issue in the outer function, because if you can't plug it into the first one, you won't be able to plug it into the second one. So let's just kind of look at some stuff. So we got f of x equals x plus 7, and g of x equals x squared minus 4. This first part says we're going to do f of g of x. So we're going to take g and plug it in to f. So we would say that that equals x squared minus 4 plus 7. Sorry. I put parentheses around it to show you that I'm inputting for just x. Okay? I can technically drop them now to combine some like terms. So this is really x squared plus 3. And then it asks for the domain. So our original input function is a quadratic, which doesn't have any issues with the domain, so all real. And then the final one is still a quadratic, so all real. Okay. Now we're going to go backwards. We're going to take, I can erase this. We're going to take f of x and plug it into g. So we have x plus 7 squared minus 4. Now when I go to simplify this out, actually, you can argue, I guess, this is just the vertex form of a quadratic, but let's just FOIL it out anyway. I need to do the binomial expansion of that. So it's really x plus 7 times x plus 7, okay? So we gotta multiply it out. So it'll give me x squared plus 14x plus 49. Then I have to bring down that minus 4, okay? So I actually get x squared plus 14x plus 45. The input is a linear function, so it's totally fine to have any kind of input, so all real numbers as the domain. Now the interesting part is when we have functions like this right here, where it's a rational function, where we have an issue in the denominator, okay? So let's try going one way and doing f of g of x. So that means we're going to take g, and I'll plug it in here. So we have 3 minus all of that x over x plus 1. Now when we have rational functions kind of like this, it is nicer to see what's going on if it's all in one fraction, okay? So what I'm going to do is I'm going to get a common denominator, which is x plus 1. Means this left term needs to have an x plus 1 in the numerator to allow it to have the x plus 1 in the denominator, okay? Now I have to distribute this 3 before I can do any like terms, and I'm out of room, so I'm going to go in this box. So x plus 1 is the denominator. And in the numerator I have 3x plus 3, and I have this minus x. And then I can combine some like terms here on the top, and 2x plus 3 over x plus 1. So the domain, got to look at the input function here, so that's this one. And x cannot be -1 because that would give us a 0 in the denominator. But also in our final answer here, we have the same issue. We cannot have a -1. So I don't have to write that twice. I can just say x cannot be -1. And I can leave it. Okay. Let's go the other way. Clear this out of the way. And we'll take this, plug it into g. So we have 3 minus x over 3 minus x plus 1. Okay, so the top, 3 minus x, and the bottom, I can combine some like terms, make that what, 4 minus x. Now in the original here, I don't have any issues here, but I do in this final function here. This denominator cannot be equal to 0, so if I set it equal to 0, I'd have to subtract 4 and divide by -1, so x cannot be 4. Okay. Let's look at some others here. Let's look at evaluating them, actually. So far, when we've done a composition of functions, we get resulted in a function. Well, now we're looking at a specific value. So I can say, hey, I can rewrite this f g of 3. So my input is g of 3. So I need to find g of 3 first. So, okay, g of x is x plus 1. I can substitute 3 in. And I get g of 3 is 4. So I can take that and substitute it in right there. You know, it's going to give me f of 4, right? So now I can take the f function, if I take the right function, substitute that 4 in, get the absolute value of -8, which is just 8. So that's kind of cool, right? And I can do it backwards and go the opposite direction and plug in f first, so g f of -5. So I need to find f of -5 first. So let's see, absolute value of -2 times -5 gives me the absolute value of 10, which is just 10. Now I can take and plug that in right here. And now I have g of 10. So 10 plus 1 is 11. It's kind of cool, right? All right, so now let's look at the decomposition of a function. So we've seen composition of a function where we are taking two functions and intertwining them. Now we are given that function. So we want to find what combination could f of x be and g of x be such that f of g of x is the function h of x that we have here. So there's a couple ways to think about things. I see things as like an outer shell and an inner shell. So to me, for this one, for this first example here, the outer shell to me is I have something in parentheses all raised to the third power. So that's my outer shell. And the inner shell is what's in the parentheses, 1 minus 2x. And that's the way I see it. So, like in this one, my outer shell is the cubed root. So f of x would be the cubed root of x. And then g of x, the input function, would be that x squared plus 1. Right? Now something like 10, number 10, I can see a couple different ways. Okay? I could see the outer shell as being 4 over something minus 1, and that something being x plus 7. Okay? Right? What else could I see? There's something else for this one. There's a reason why I wanted to do this. We could say that this is x minus 1, and g of x is 4 over x plus 7. So, either one is fair. So, there we go. And I'm going to stop it here to make a second one, because these aren't really all that combined.